Okay, this video is going to talk about the size of an atom. And the size of an atom is determined by the electrons because the other particles, protons and neutrons, are in the nucleus of the atom. So they're in the center, so they won't determine the size. What determines the size is where the electrons are, which orbit or orbital they are in. Okay, orbit is just a term for the Bohr model. So orbital is the right description, and so if we label our orbitals according to n value, the smallest n is close to the nucleus, n equals 2 is a little further out, n equals 3 is a little further out, and so depending on what n level you're in will determine the size of an atom, and there's also other criteria that I'll mention in a couple minutes. So let's look at just one specific n level. Let's look at n equals 2. Okay, so this approximate distance from the nucleus, and n equals 2 has both s and p orbitals. So the s orbital is spherical, and the p orbitals are lobed. So there's a px, there's a py, actually I have them backwards, and then there's also a pz, so it's all three-dimensional, and they all fit in this area that is a certain distance from the nucleus. All right, so let's use these ideas to talk about going down the periodic table and going across the periodic table, so we can see the trends in size as you move across the periodic table. All right, going down is the easy one. If you look at the electron configuration for lithium, it has a helium core that is filled, and it has a 2s orbital with one electron in it, which I've drawn here. That's the 2s, spherical, and I've got an electron in it. If you look at sodium, it's one row down. It's in the same group. Its configuration is neon with a 3s electron. Okay, a single electron in the 3s. So the difference is that they have filled cores, filled noble gas cores, but this one has its outermost electron is in the n equals 2 level. This outermost electron is in n equals 3. Keep on going down the group, and you have potassium, which has this configuration. And so you can see that you're going up in n as you go down a group. So you're going from period 2 to period 3 to period 4, and they get bigger and bigger because they are in larger n values. Okay, so that's a fairly understandable trend. I will summarize that below with when you add an additional electron, or when you go down a group, the additional electrons are in higher n, so they are farther from the nucleus. And we can explain this also in terms of shielding the inner electrons, like say the core, like in this case the argon core, shields this outer electron from the nucleus so that it can be in a further out orbital. So we say this has high degree of shielding. Oops. Shielding. Okay, didn't spell that so well, sorry. All right, and then now let's talk about what happens when you go across the periodic table. When you go across, you are in one period, but different groups. So let's look at phosphorus, sulfur, and chlorine, which are in a row in period 3. Okay, I'm going to draw the rest of the p orbitals, px, py, and pz. And for phosphorus, we have 3 electrons, so I'm going to put 1 in each of the orbitals. And they aren't actually confined to one lobe, that's just where I'm drawing them. Okay, and then now let's look at sulfur. It has 1 additional electron. I'll draw the pz. It has 4 electrons, so one of them has to pair up, and I'll put it as a spin down. Again, this is one orbital with 2 electrons, and they aren't actually in the 2 different lobes. I'm just drawing them that way. All right, and then chlorine has 1 more, so we'll draw electrons in these, and the others have to be spin down because if they're in the same orbital, like these two are, they have to be opposite spin according to the Pauli exclusion principle. All right, so let's talk about what's happening with size as we go across. They're all in the same orbitals. All the electrons are in 2p orbitals, so you're not changing n value, you're not even changing L value. And the M sub L value, which is orientation, doesn't affect size, just affects direction they're pointing. So the difference is that while you go across, you're adding electrons to the same approximate distance from the nucleus, still the 2p, but you're also adding protons to the nucleus at the same time. So each of those additional electrons is not shielded nearly as well from the nucleus as they were in this case, where the electrons were inner electrons, creating a lot of shielding. So these electrons do feel the pull of the nucleus, and you're adding more and more protons. So actually, as you go across, the atoms get slightly smaller. You have more electrons, but they're pulled in slightly more tightly by the more positive nucleus. So let's summarize that. As you go across, the additional electrons are in the same N levels, and so the more positive nucleus, okay, you get a more positive nucleus because you're adding protons at the same time, pulls them in tighter. And that creates a slightly smaller, so they're smaller going across. And this is because the shielding is not so great. I should say over here, as you go down, they get larger. Okay, so as you go down, they get larger. As you go across, they get smaller. All right, let's look at that trend on the periodic table. Okay, so here is the periodic table with the atoms drawn with, showing the relative size. For most atoms, the noble gases are left off the list. So notice, as we said, that as you go down a group, the size gets larger. Okay, and that's true for this group. The transition metals show the trends, but only to a minor extent. So we mostly look at the main groups. This gets larger, this one gets larger. Okay, they get larger going down because they're increasing in. And as you go across, you will see that they get smaller. Lithium's bigger than beryllium, is bigger, then they get smaller. Okay, so as you go across, there are some anomalies, but in general, size increases as you go down. And since it decreases going across, we can also say that it increases going to the left, so that in this corner is where you have the largest size. And you can remember that. And then in the opposite corner are the smallest atoms. Okay, so we can use this information, and you should learn the trends, this trend in the size. You can use it to compare different atoms. So let's go down and look at some problems for you to try. I want you to rank each of these three groups according to size, which one's greater than, which one's the greatest, the middle, and the smallest size. So do that, and then we'll talk about those. Okay, the first one was calcium, strontium, and magnesium. Okay, so we see calcium is here, strontium is here, magnesium is here. So going down, they get larger, so we can say that strontium's the largest. And next is calcium, and next is magnesium. So that's A. Try B, which was calcium, potassium, and gallium. So calcium again, potassium, and gallium's way over here. So again, you should do this with a periodic table that doesn't show size. You should be able to predict it just based on position. And we can see that calcium is to the left, so calcium is the biggest, or sorry, potassium is the biggest. Calcium is the middle, and gallium is the smallest. And finally, so that's the first one was doing down a group, the second one was across a period, and the third one is a combination, calcium, rubidium, and strontium. So look at them, that calcium, rubidium, and strontium are these three, so we're comparing down a group and across a period. We know that rubidium is greater than strontium because of the period trend. Okay, so we know that much. We can write that much. Rubidium is larger than strontium. And we know because of the group trend that strontium is larger than calcium. So we can rank those this way.